This is an update on my Turing Welchman Bombe project that I've been working on for quite a large chunk of this year, actually. For those who haven't been following my blog, the Turing bombe was the machine that the British used to help crack the Enigma codes during World War II. What I've done is basically figured out how that machine worked and created my own desktop version running in software. Now, if you want to know more about the bombe, there's plenty of information on my blog explaining how it works and how I did all this, as well as lots more information online. But I would recommend, if you're interested in it, getting this book, which is kind of like a simple introduction to the bombe. And this is produced by Bletchley Park and is available from them or from their website. I definitely recommend it. It's worth getting. We can see that my bombe is completely self-contained. It's in its own housing. It doesn't need connections to anything, and it has its own battery inside, although you can run it on an external power supply. It's fairly portable. It has got a handle on it. It's quite heavy. It weighs about 10 kg. It's all made of steel and similar materials to what the original is made from. Now, I started building this after first completing my Enigma machine watch project, because to understand how the bombe works, you first need to understand how Enigma works. I won't really go into explaining how it works here because it is horrendously complicated. So I'll just give a quick overview of how the machine works. As I said, it's a steel casing, steel frame just all welded together, and steel panels on the outside all painted in the correct crackle finish black wrinkle finish paint. The drums I have are just the 3 indicator drums. If we have a look in this book, you can see a picture here of these are the 3 indicator drums, and this is the start-stop buttons, which I have here. This also shows the indicator unit on the side of the machine, and I have similar here an LCD screen as the indicator unit. I've just made a mark on the machine. That's okay. Now, my drums are slightly smaller than on the original. One, because I didn't want it to be too big because it has to fit on a desktop, obviously. And 2, because I made the drums out of basically what I had lying around, which were some metal sweet tins. And they turned out to be 3/4 scale, so when I made all of these different parts and bits and pieces, I made them 3/4 scale. But they are accurate copies of the original bombe, as far as I can make by hand at home anyway. So you can see at the moment the drums spin fairly freely. They're powered by stepper motors, which we'll have a look at in a bit. Probably the best thing to do is actually turn the machine on, and we can see what it does. So, as I say, I wrote my own code in C++, and that's running on a Raspberry Pi 2. Now that's talking to an Arduino, which is driving the stepper motors. And these should go through a startup sequence in a second. Any second now. So now that the machine is started up, these motors are powered and are holding, which is now why the drums click around. So what we can do is set up the machine to the correct starting position, which is ZZZ. That's what these are. These are actually little finger holds to rotate the drums around. Now these drums are exactly like the original ones, so they will actually come off. These are little spring clips, these little rabbit ear things. And you can take these drums on and off, but because the indicator drums don't need to come off, I just have them attached permanently, more or less. So we set the machine up to ZZZ, and we can choose what menu we want to run. Now the menu is effectively how you configure the machine, and on the original machine it was done with physical wires in the back of the machine. Now I don't do that. I have my own file format to specify the menus and how they're configured, and I have all of those stored on a little USB stick. So when the machine starts up, it mounts that USB drive, and then it lets you select which menu file you want to run. And I have a number of those on here. We can step through them, and basically we will run the same menu that they use at Bletchley Park to demonstrate the real bomb there. So that's called the weather report menu. We can select that, and the machine is now ready to run. So if we press start, off it goes. Now this particular menu has two stops. The first one is at DKX, which, if you note on the drums, because they're going backwards and we start at Z, that's not too far around. So that'll actually stop in a minute or so. While I'm waiting for that to happen, I'll just explain a bit more about the motion of the drums. So as I say, these are driven by stepper motors, and it's basically running through all the iterations of the 3 combinations of the drums and the 26 letters on each drum. So most people would assume that the top drum does 1 revolution and then the second one will step. It's not actually the case. If you look very closely, you'll see it's doing a revolution and a half before the second one steps. And that's because the original machine was mechanical, and as these drums move, wires and contacts need to move into position, and that gives it time to do that. We're coming up to the first stop now. So the machine is now stopped, giving us one of the potential solutions, and you can see, hopefully, that it's on DKX. Now if we spin the machine around and have a look at the indicator unit on the side, we can see that it's indicating on Q, which is basically giving us part of a possible solution. I won't go into exactly how all that works. It's quite convoluted. The machine, unlike the Hollywood descriptions of it, doesn't just spit out the answer to the code. There's actually quite a bit more work that has to be done. But we can now set the machine running again. And while that's happening, we can have a look inside. Now, my camera only lets me do films up to 10 minutes long, so I will stop this and we'll restart and have a look in the back of it. Okay, let's spin this thing around. Just like the real bomb, mine has little wheels on the bottom, which are actually very handy. So if we open the back of the machine, you can see inside here all the electronics for it. So if we start at the bottom, down here I've got a sealed lead acid battery, 12 volt battery, and this is just a voltmeter showing me the battery voltage. The machine does draw quite a bit of current. It's between 1.5 and 2 amps when it's running. Down the bottom here we have the Raspberry Pi 2, and next to it is that USB stick that actually has the menu files on it. Just above that is the Arduino, and it and the Raspberry Pi are connected to an interface board that I made up here. Now this does various things. One is it lets me connect everything together, and it also does the level shifting that's necessary between the Raspberry Pi and the Arduino, because the Arduino uses 5 volt logic and the Raspberry Pi uses 3.3. So I have some little buffer stages here that convert the levels as appropriate. Over on the side here, you can see the interface board connects to 3 driver boards, and these are what is driving the stepper motors. Now we can't actually see the motors, they're sort of mounted on the front panel here. So the 3 motors are behind here, behind the 3 drums of course. You can note in here as well that I've tried to keep to the original wiring style. They used a lot of red wires in the bomb for some reason, and these are all cable laced together, which means there's actually string just holding all the bundles of cable together, rather than using something like cable ties. This also gives a good view of the frame. This is just steel furniture tube welded together, and the panels are all just screwed on. So one of the things on the interface board is the how I do the drive signals for the 3 stepper motors. So if we close this up, rotate it round again. The next stop is at FAN, and you can see the bottom drum's up to Q at the moment, so there's a little way to go. Now, when I drive these stepper motors, these are 4-wire steppers, and to drive a stepper motor you send it a sequence of signals which causes the motor to step around. It physically moves in steps. Now these motors have 200 steps per revolution, and I'm actually micro-stepping them, which means I'm doing half steps, so I get 400 steps per revolution. Now it took quite a bit of cunning code to be able to move the drums accurately 26 positions, because 26 doesn't divide into 400 very well. So there's quite a bit of fiddling around to get that to work. And the other tricky thing is to get the 3 drums to move in sequence. Now to do that, instead of driving all 3 drums individually, effectively I have one set of drive signals, and they're going to this top drum all the time. And then at the appropriate times, through a sort of latching buffer, I switch the same drive signals to the 2nd and the 3rd motors when appropriate. So everything moves in sync, because it's very important the whole thing keeps in synchronization really well over the course of a run. And a whole run can take about 20 minutes. So this bottom drum is now in the correct position for this next stop. We just wait for the middle one to get round to A again, and we should see it stop. Now when it stops, I simulate the real bomb slowing down, which is why you'll see it. This top drum will actually go past the position and rotate at half speed to get back to that stopped position. It should happen about now. So we can see here it's on F-A-N. And if we look at the indicator, it's showing us K. So now we can just let this continue to the end of the run. Now the machine, as I say, is all completely self-contained, and when it gets to the end of the run, it will actually shut itself down. So it starts up, you select the menu to run, you let it run, and then it will shut down. Now this is running almost at the same speed as the Bletchley Park bomb. I am actually running a little bit slower, because there's only a certain maximum speed that you can actually get these stepper motors to step and maintain accuracy. So I'm running fractionally slower than the one at Bletchley Park, but I do believe that one is running a little bit faster than the original World War II ones. It's slightly over speed, but it doesn't really make much difference. So as you can see, this will just sit here now. I do cheat a little bit. Because I'm pre-calculating all the stops, I already know that it's actually finished, and now it's just going to run to the end. Of course, in World War II, when they were running these menus on the machines, they didn't know what stops they were going to find, so they would have to let the machine run to completion. We'll let this one run as well. And that's about it, really. So, as I say, I've got multiple menus in there that I can run on it. This is the same one they run at Bletchley Park. And I think this one was chosen, one of the reasons it was chosen is because the first stop only takes a few minutes to reach, rather than having to wait a whole 20-minute cycle. Some of the other menus I've got from various books about the bomb. and most of them are actually test menus that came from an original 1944 US Army report on the bomb. And that particular report was very handy in trying to understand exactly how the machine worked. As I say, it's actually a very, very complicated machine. Although what it's doing is comparatively simple mechanically. To actually get it to work is a lot of work, but effectively it's just a giant circuit tester. Now, as I say, this machine by itself doesn't give you the solution to the code. That takes quite a bit more work, and there is actually a whole other machine known as the checking machine that they use to do that. But this basically took away a lot of the physical mechanical work that would have had to have been done to try and figure out what the daily settings were for the Enigma machine. And that's effectively what this is giving us. Is it gives you which rotors were used, which order they were used in, what the ring settings were, and what one of the plug board partners is. And that's effectively what the indicator unit on the side is showing you. So as I say, it is a very, very complicated machine to get your head around. And it's very good to actually see it running and have it running accurately, finding the correct stops, managing to keep itself in sync. It's been quite a satisfying project. It's actually also quite hypnotic to watch and listen to. And this one isn't quite as noisy as the original one, if you've ever seen the original at Bletchley Park, which is all driven by gears and cams, and that makes a very impressive noise. So as I say, this would now just keep running to the end. I think my camera is going to run out of film time before it actually gets there, but basically it'll get right to the end, back to ZZZ, and stop. And that whole run takes just over 20 minutes, which is the same as the original. So we can see we're up to D, so it's almost there. And then the machine will shut itself down. And that's basically it. Now that it's finished, you can stop it, and the Raspberry Pi will shut itself down. It's actually a little bit difficult to know when it's stopped. If you connect the machine up to the network, which is what this little panel here is for, that lets you get access to the network port on the Raspberry Pi, which is used for debugging and on that, you can tell when it's shut down because the network connection goes down. But other than that, I just leave it for a few minutes and then turn the power off. And that's it done.